Hello everybody, I welcome you all for this video lecture on Lanthanides contraction and its effects, which is the second part of inner transition elements in the General Chemistry 3 paper of BSc Chemistry course at Dr. MGR Educational and Research Institute. The 14 elements following lanthanum in group 3 of periodic table with atomic numbers of 57 to 71 are listed in the table. From lanthanum to lutetium, overall there are 15 elements in the first F block series. Since all these 14 elements resemble lanthanum in chemical properties, they are called as lanthanides. The lanthanide series element starts from lanthanum and the symbol is La and the atomic number is 57. The following elements of lanthanide series are cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, herbium, thulium, ytterbium, lutetium. Lanthanides are found as oxides along with other minerals, and so they are called as rare earth minerals. They are abundantly in lithosphere. They are mostly found in the Scandinavian and Soviet Union USA islands. Many minerals have their deposits, but monazite is the most important one of it. Monazite is a dark heavy stone of various composition of these lanthanides. It is the lanthanide orthophosphate and significantly has 30% thorium. Lanthanum, cerium, praseodymium and neodymium occur as individual minerals of about 90% with yttrium and the remaining compositions with other heavier elements. Promethium occurs along with uranium ores. So the pictures of the Scandinavian, Florida islands of USA are shown in the figures. Also, the monazite mineral is also being picturized here. Lanthanides are found as oxides along with other minerals, and so they are called as rare earth minerals. They are abundantly in lithosphere. They are mostly found in the Scandinavian and Soviet Union USA islands. Many minerals have their deposits, but monazite is the most important one of it. Monazite is a dark heavy stone of various composition of these lanthanides. It is the lanthanide orthophosphate and significantly has 30% thorium. Lanthanum, cerium, praseodymium and neodymium occur as individual minerals of about 90% with yttrium and the remaining compositions with other heavier elements. Promethium occurs along with uranium ores. So the pictures of the Scandinavian, Florida islands of USA are shown in the figures. Also, the monazite mineral is also being picturized here. In this slide, we see the pulling the rope game. Now in this game, we'll have two teams on either side of the ropes and each team have to pull each other. The team that pulls the other team to its side wins the game, and the other team that is being pulled off to the other side loses the game. So we all know this game very well. So that has been picturized in the first figure. In the second figure, we can see instead of the team on the left side, we have a giant bull, picturized a giant person like, and in the other half, that is the right hand side of the team, there are few persons. Now if we consider the giant is very heavy, hefty and very strong enough to pull the other team, he is going to win and the team on the right hand side is going to lose. But the thing is, if we consider all the small children on the right hand side are very hefty, bulky and very much stronger, the chance of the right hand side team to win probability is more for it. Now what I am going to take this as an example for is, if the left hand side, the giant person, is a nucleus that has both neutrons and protons. Okay, so the strength of this nucleus is being compared to this giant person. The right hand side team comprises the electrons in each subshells and the shells. So if the smaller children, the children are considered as electrons occupying the S and P subshells, and the elder persons are electrons occupying the D and F subshells, then we can say that if more children are there, that is, if more electrons are in S and P subshells, easily the right hand side team going to lose. That is, the electrons will be pulled towards the nucleus very well if the electrons in S subshell and P subshell are more. In other words, if the electrons in D subshell or F subshell are more, there will be a screening effect between the nucleus and the outermost electron. In this picture, if the blue t-shirt person is the last electron in the F subshell and the rest of the persons before him are the electrons in electrons in the S and P subshells, then the power of the last electron being pulled towards the nuclear charge depends upon the electrons occupying the S and P subshells. If more electrons are in the S and P subshells, then the outermost electron in the F subshell is going to be pulled towards inside in case of lanthanides. In such cases, there will be decrease in the atomic radius, and this atomic radius decrease ultimately results in contraction of the whole lanthanide series from lanthanum to lutetium. Because when we go from lanthanum to lutetium, the atomic number increases and the effective nuclear charge also is going to increase, because the last electron in each atom is going to be added only to the F subshell, outermost F subshell. So consequently, the electrons inside the S and P subshells are going to be the same over the series, and so the screening also will be very less. So the nucleus can very well pull the outermost electrons towards it. As a result of this, there is going to be a contraction. So this is what we call it as a Lanthanide contraction. Now what we have seen as an example is given as statements here. Now lanthanide contraction is a significant and steady decrease in the size of atoms and ions in lanthanide series with increasing atomic number. So when we go from lanthanum to lutetium, the atomic number is going to increase and the size of the atoms or the respective ions is going to decrease steadily. So this lanthanum, in the lanthanide series, lanthanum has the greatest atomic radius and lutetium as the smallest atomic radius. We can also see in the graph below. As we proceed from lanthanum to lutetium, the nuclear charge and number of 4f electrons increases by 1 at each step. So the effective nuclear charge experienced by these 4f electrons increases, and so there is reduction in size of entire 4f shell. The accumulation of these successive contraction is the total lanthanide contraction. So we can see in the figure also very well the steady decrease of the ionic radius or the atomic radius. Now what is the effects of lanthanide contraction? Because there is contraction in the lanthanide series, the decrease in the atomic and ionic radius, what is going to happen? What is the consequence of it? Is what has been given here. First is the magnetic properties of lanthanides. When we see the lanthanide series, the lanthanides have less shielding effect by the electrons in the 5s and the 5p shell for the 4f electrons. That is, the overall nuclear charge or the effective nuclear charge on the outermost electrons are high because the electrons in the inside 5s and 5p shells have very less screening or shielding effect. And so the external magnetic forces on the f electrons are less. Why the external magnetic force is very less on effective electrons is because the effective nuclear charge of the atom is more on to the 4f electron. So the 4f electrons will experience lesser magnetic forces from the external side. Also, they have more unpaired electrons giving rise to larger magnetic moments. So generally when we see the lanthanide series, they will have more unpaired electrons. So they will have larger magnetic moments. So that has been found out and is also been plotted as a graph on the right hand side. If there are no unpaired electrons, the species will be diamagnetic. So when we see the ions of +3 oxidation state of lanthanum and lutetium, they have no unpaired electrons. So they will be diamagnetic. Whereas when we see ytterbium and cerium of +2 and +4 oxidation states, they also don't have any unpaired electrons, and so they also will be diamagnetic. Whereas the rest of the elements will have unpaired electrons contributing to paramagnetic character of the atom or the ion. And the next one here we are seeing are the spectral properties of lanthanides. Now the colors of these lanthanides are because of FF transition of electrons. Because there are more electrons in the f orbital, transition is going to take place, and because of the transition, the atom or the ion will have a fluorescence or luminescence character. So because of these spectroscopic properties, especially fluorescence and luminescence behavior of certain ions, they are also used as activators in the laser principles. Now their oxide phosphorus, that is the lanthanides oxides of phosphorus, are used in color television tube. Neodymium compositions are used for laser activity. So they are also used as probes in biological systems. Here we see the summary of lanthanides contraction by seeing the ionic radius of the lanthanide series. So lanthanum is having an electronic configuration of 5d1 and 6s2, outermost electronic configuration we are referring to, and the ionic electronic configuration is just xenon. It will lose the 5d1 electrons and 6s2 electrons. So having that, it comes to it has a radius of 1.061 at Armstrong units. And down the series, next is the cerium. Its ionic radius is 1.034 for cerium 3+ again. And praseodymium 3+, it has 1.013 Armstrong units. So when we see the atoms in the +3 oxidation states, the ionic radius decreases gradually, and to lutetium it reaches to 0.848 Armstrong units. So we can very well see that there is a decrease in the ionic radius. This kind of a decrease is what we call it as a lanthanide contraction. And the oxidation state of these atoms will be mostly +3 because they are highly electropositive and they can readily form +3 ions. They show oxidation states of +3. Cerium shows 4+ also, whereas samarium, europium, ytterbium show +2 as well as +3. Now decrease in radius down the series shows the contraction because of, as we said earlier, increase of electrons in 4f shell as the atomic number increases. Secondly, because of increase in the effective nuclear charge over the 4f electrons, and ultimately because of the less shielding effect of 5s and 5p electrons. Here we end up this video presentation of part 2, Lanthanide contraction and its effects of inner transition elements. So far in this video lecture we have seen what is lanthanide contraction and its effects. So the magnetic and the spectral properties of lanthanides are because of the lanthanide contraction. The oxidation states of lanthanides are mostly +3. So this is what we have seen so far in this video lecture. Let us meet in our next video lecture. Thank you.